So let me just remind you of the last thing we had proved last time, because we will make use of it in this lecture again. So the last thing we had proved last time was, if you remember, so we talked about the group of rotations. We said in the Lie algebra of the rotations, there was only, if we look at the subset of elements that commute with each other, there was only one element inside that set. You could pick what you wanted, L, X, L, Y, or Z. And when we took that element, a single element that commuted, we formed the group element that would generate rotation. So this would generate rotation of the angle theta. In case I looked at that yesterday. About the z-axis, we took the trace, and this gave us the character for this rotation and in angular momentum representation now. Then what we were able to show was, if we took the tensor product of L1 with L2, z hat theta. So we argued just as a property of tensor products that this was a product of the characters. And then we argued that in actual fact what this ended up giving us was the sum from L is equal to the mod of L1 minus L2 L1 plus L2 by L z hat. And we said this was the familiar addition of angular momentum rule in quantum mechanics, that L1 tensor L2 is equal to a direct sum of some spins L going from L1 minus L2 up to L1 plus L2. Physically, what does this correspond to? If I have two particles and I want to describe the two-particle wave function, the way I go from two one-particle Hilbert spaces to one two-particle Hilbert space is by taking the tensor product. So the idea here is I had one particle with a spin L1, a second particle with a spin L2. So those are the spins of the two particles. That's the L1 and the L2 appearing. And then I ask the question, if I measure the angular momentum of this two-particle system, what will I find? And the possible angular momentum of this two-particle system are these values L that we're sitting here. We now want to ask precisely the same question for the conformal group. And let me give you an example of the triangle that you'd like to see. So we said that the free scalar field, in this case, there were three elements in the Cartan subalgebra. There was the dilatation operator D, and then we said there were two operators coming from Lorentz. And I told you to think of this as J3 left and a J3 right. So that was the piece that I didn't justify in detail for you. The Lorentz group can be broken into a product of SU2 times an SU2 to two sets of rotations. And I'm using the J3 of those two sets of rotations to label the states. If you tell me what is the value of D, J3 left and J3 right, I know what the state is inside the representation. For the free scalar field, we said the primary operator, remember the one of lowest dimension. So the primary had D was 1, J3 left, J3 right was 0. What we would like to understand today is what you get when you take the tensor product of 1, 0, 0 with 1, 0, 0. Now what is the relevance of this? If we call the field from our CFT phi of t, let me just call it phi of x, that's got a time and a spatial set of coordinates in it, and I multiply by a second field, phi of y. So I've just multiplied these two fields. The possible representations that I will get of the conformal group are whatever I get from this tensor product. And what is very interesting is the following. Here we are looking at 3 plus 1 dimensions. So I wasn't going to mention this, but seeing as Alvaro just told you about ADS, let me mention it. If you're in 3 plus 1 dimensions and you're studying a CFT of the free field, okay, this is a field that you could introduce in the CFT. It's a bilocal field, you can call it, if you like, sigma of x and y. And when you study how this behaves under the conformal group, so you now know that for us this will be SO42. All of the representations that you will get here are the representations that appear in that tensor product. If you now go to ADS 5, the isometry of ADS 5 is SO42. So notice here we were in 3 space and 1 time dimension. Here we're in 4 space and 1 time dimension. And if you look at what is the spectrum of fields, the spectrum of fields that you get are precisely all of the representations that will appear here. That's what we'll work out. This is the first, most basic piece of evidence for what is called higher spin duality. Okay? So that would be the physical application of this result. And we'll see that to it. But what I want to do now, remember yesterday we used characters to derive this tensor product formula. So what I want to try to do now is, let's calculate the characters of the conformal group. And this would be the same in basically any number of dimensions. We would do it in the same way. So we're going to do precisely the same logic that we had here. We're going to write down a group element. That group element will be obtained by exponentiating elements of the algebra. And the only elements of the algebra that we will exponentiate are those that belong to the Cartan subalgebra. The Cartan subalgebra is the biggest algebra of elements that commute. The eigenvalues of those generators completely label the state. So what we want to calculate now, let me still call it chi. I'm going to imagine a field, a field of spin 0, that's all we're going to need for now, and of dimension delta. And what this character will be equal to, it will be a trace, and now we will have e to the I, let's say t, times the dilatation operator. That's the first thing inside our Cartan subalgebra. Plus I, we can say theta left, j3 left, plus I, theta right, j3 right. So that's the trace we would like to calculate. Now remember we said there's a state operator correspondence. I'm going to start writing down the operators and the states that would appear inside this multiplet. So for the primary, we would have some operator O, corresponding state, let me just call it like that. And the properties it would have is D on O is minus I delta O, and J3 left on O would vanish, as would J3 right on O. Both of those would be 0. So that's the primary. What's the next state in this representation? How do I get it? P acting on the state. Good. So if we're thinking about the operator, act with the commutator. If not, act with P mu on the state. Now, I'm going to start using some things from the Lorentz group. I'm not going to prove this. If you've seen this before, that's great. If you want to know how to prove it, we can chat about this later. I'm not going to prove it in this lecture. What it is, it's the following. Take a tensor, mu1, mu2, up to mu k. So it has k indices. It is symmetric. So by that I mean I can swap any two indices and the tensor doesn't change. And it is also traceless. And by that I mean contract any two indices with Minkowski metric and you'll get 0. This thing, as a representation of the Lorentz group, has a certain spin. Okay, let me check. Someone who should know. Celeste, what is it?
Sorry, what is the question again?
What is this representation of the Lorentz group? Mirina? Good. K over 2, K over 2. So a tensor that is symmetric and traceless transforms in that representation of the Lorentz group. In particular, here we have a single index. It's obviously symmetric. It's obviously traceless. So this would be in a representation of 1/2, 1/2, as far as J3 left and J3 right goes. Now, let's go one further. What's the next descendant? Act with two p's. So the next descendant will be p mu1, p mu2, O. If I've got these two indices, what can I form? Well, I can form a tensor that is symmetric and traceless. So one of the representations I will get using that formula is 1, 1. But I can also take the trace of these two, contract mu1 and mu2. And if I do that, I'll form this operator. P mu1, well, let me just call it P mu mu, eta mu1, mu2. The eta you forget about, that's invariant. So this looks like something that's got spin 0, 0. Okay? And we just have to enumerate all of these states. So what I have to do is I have to look at the indices that appear. Here I've got two indices for the momentum, and I have to decide what kind of tensors I can form. The momenta always commute, so whatever I'm going to get is going to be symmetric. But the point is, I can take traces of p's to get tensors of lower rank. So here I had a tensor with two indices. By taking a trace, I can produce, so look at that piece to get the eta. This is an operator that has no indices. You could also think that this is the primary that I'm looking at there. So you could imagine me breaking things down like this. Okay? I don't want to write this the whole time, but let me write it once. You could imagine me, let's keep that. You could imagine that I have written the following down. P mu1, P mu2 minus eta mu1, mu2 over d, P mu on the primary. That's only got two p's acting. If you contract this with eta mu mu, it is clearly traceless. And the extra thing that I haven't put in, I can include separately, is just p mu on O. And you can see that he doesn't have any indices. That's another way to think about it. Okay. This would be spin 0. This would be spin 1, 1. We would have gone for the symmetric traceless tensor. Okay. You've got 30 seconds. I want to know at the third level, where I can have stuff like this appearing, let me say minus traces. So perhaps I'm thinking in this way. Is that the full set of operators I can get? What else can I get? So I'll give you 10 seconds. This was delta. I should have said this dimension is delta plus 1. We've got 1p acting. This dimension over here would be delta plus 2. Both operators, each time we have a p, we increase the dimension by 1. Here we would have delta plus 3. Okay, who can tell me what possible spins we can get? With 3 indices, what do we have? Jeff? Very good. So we've got a 3 over 2, 3 over 2. Is that it? Anything else? Leila, you look like you want to say something? Laura, is that it? Narina, what else? So we can also have, what did we do here? We were allowed to contract indices in pairs, right? If I contract one pair of indices here, what kind of stuff would I have? I would have a P mu, a P alpha on O. What does this look like? As a tensor, this looks like T mu. That image doesn't transform. One index means I'm talking about 1/2, 1/2. So those were 2 possible angular momenta. Okay? So you guys did not convince me you know what's going on. It's, I would say, wasn't even close. So now let me give you another example, and I want to know what are the spins for this example. So the next table, P, mu1, mu2, mu3, mu4. So now we're at 4th level. That's one of the operators. What spin will that one have? 2, 2, good. Now, what else? 1, 1, great. And 0, 0, fantastic, good. Okay. And all of these have got delta is equal to 1, 2, 3, 4 plus, d is equal to 4 plus delta. Okay. That's the dimension. Good. Okay, guys, are we happy with that? Now, what we want to do, and you can keep going, right? You can keep going, it goes on forever. Now, what we want to do is, we want to take the trace of some sort of an operator like this. So let me not take the trace. I'm just going to sandwich one state on either side of this. And when we figure out what it looks like for one state, then let's figure out what we should get for the trace. So the state I'm going to consider is maybe, you know, that nicest one that we've got so far, 2, 2. So let's say we've got 4 plus delta, comma, 2, 2. That's the state. Now we will have our exponential, e to the I t plus I theta left, j3 left plus I theta right, j3 right. And then we'll sandwich the same state here. 4 plus delta, comma, 2, 2. So that's the matrix that we're looking at, diagonal matrix. So what happens is, when D acts over here, we just pull out the eigenvalue. So that's the easy piece. So let's deal with D. So we get E to the I, T, and when D acts on the state, remember, we get minus I times delta. So we'll get minus I, and then 4 plus delta. And now we need to be a little more careful, because you see, even though I've written this as one state, this isn't really one state. Okay, it's many states. So let's see why. when we write this state, 4 plus delta 2, 2, for all of the states that I'm studying, D acting on the state will give us minus I times 4 plus delta. So I'll just write D is equal to 4 plus delta. If I act with J3 left, the possible values I can have in a spin L multiplet, I go L, L minus 1, L minus 2, all the way down, minus L plus 1 down to minus L. So here I would have the minus 2, minus 1, 0, 1, 2. And precisely the same thing for J3 right. Okay? So it's not just one state that I have. Here, this can take one value times by 1, 2, 3, 4, 5. 5 values times by 1, 2, 3, 4, 5. 5 values. So there's a total of 25 states inside this representation that I'm looking at here. When I sandwich this here, I mean sum over all 25 states. When I sum all 25 states for J3 left, I'm just going to calculate the character that I calculated yesterday for rotations. So this will give me the character, let's call this for spin 2. And this will be a function of theta left. And when I do the trace over the right states, I'll get the character for spin 2 of theta right. And that's what I would get for this particular state. I'm going to introduce a new variable. I'm going to say, let's make it here. S is going to be equal to e to the power of t. And then what I've gotten here is S to the 4 plus delta chi 2 theta left chi 2 theta right. Are we all happy with that, guys? Anyone that would like to ask a question on that?
Can you repeat the explanation for chi 2 theta left?
Sure. So what we're doing here, remember what we did yesterday, okay? So yesterday we were doing the following. I'll put it here. Yesterday we were calculating characters of the rotation group, right? And there we had L, M, e to the I theta, J3, L, M. And we summed from M was equal to minus L up to L. The eigenvalue would have been plugged into the exponential. The state is normalized. So you just got to sum of these exponentials running over the allowed J3 values. But here, after we plugged in the eigenvalues, the state will hit here, it's normalized. And then we've got to sum over the allowed J3 left values, the allowed J3 right values. But that just gives us the character that we had yesterday. Happy? Good. Okay. So now, let's start calculating this character. Okay, so chi delta naught is equal to 3. The first state I can plug in has dimension delta, J3 left is equal to naught is equal to J3 right. So the contribution I will get will be S to the delta. You see here my dimension was 4 plus delta, so delta just gets plugged in there as the exponent of S, because it picks up the eigenvalue. And then I'll pick up the character for the left spin and the character for the right spin. But this first state is spin 0. So I can write chi naught of theta left times by chi naught of theta right. They're both spin through. Plus, so now I've taken this state in the trace. Now you need to trace this state. Now for this state, the dimension is delta plus 1. So we'll get S to the delta plus 1. The left spin is 1/2, the right spin is 1/2. Chi 1/2 theta left, chi 1/2 theta right. Plus, we'll write down a few more terms because then we'll be able to guess the formula. Okay? So we've done that state. For the next state, delta plus 2, we'll get S to the delta plus 2. We can have spin 1,1 or spin 0,0. For the spin 1,1, we'll get chi 1 of theta left, chi 1 of theta right, plus S to the delta plus 2, chi 0, theta left, chi 0, theta right, plus. Okay, guys, that was delta plus 2. Now, will you please write down delta plus 3? Okay, who's going to tell me the answer? James, you're smiling, or you're being friendly, or you've got an answer?
So it's S delta plus 3.
S delta plus 3.
Chi 3 over 2 theta left.
3 over 2, theta left. 3 over 2, theta right, good. Plus?
Plus S delta plus 3 chi.
Good.
Half theta left.
Great, absolutely. Now, sorry guys, I don't want to belabor the point, but I'm going to want to extract a pattern. So I want you to do one more, delta plus 4. Let's just write that term down, and then we'll extract the pattern. Okay, so I've written up the delta plus 4. If you agree, fantastic. If not, let's chat. Now, let's see what's going on. So my first term is S delta chi naught. So let's put S delta chi naught of theta left, chi naught of theta right. And that is that term. But hang on, here I've got another chi naught. Let me start factorizing. So I've got 1 for this term. For this second term, so that's term 1, that's term 2. Oh, and I've got another one. There. This is for term 3. Why is this happening? It's happening because when I act with p mu on the state, I don't change the spin of the state, but I add dimension 2. So this, I haven't acted with anything. Here I've acted with the p mu. Here I've acted with the p mu squared. So in fact, this would carry on forever with all of the even powers, because I can add a p mu cubed, p mu to the 4, and so on. So that's the first term. Are we happy with that, guys? Now let's put the second term. Let's go S delta plus 1 chi 1/2 theta left chi 1/2 theta right, and that is this term. That's the 1/2. It shouldn't surprise you now that look, 1/2 appears again. So let's call this one A. So that's A plus, and now look at B. The second term here, it just has an extra S squared. And same reason. To get this term, you've got a p mu and a p alpha acting on the state. So again, this would go off. The next term you would get is an S to the 4, and so it would continue on forever. Then we've got an S to the delta plus 3. Delta plus 2. Chi 1/1. And again, the same argument tells me, I can always act with contracted derivatives, so I'm going to get multiplied by that polynomial. And so it continues. So now let's write a nice formula, which just gathers those terms. These brackets that I'm multiplying the whole time over here, so let's say equals. These brackets that I'm multiplying, this is just the sum from p is equal to 0 to infinity of s to the 2b. Look at the first factor. I've got s to the delta 0. Now, delta is increased by 1, I've got 1/2. Delta is increased by 2, I've got 1/1. So the spin is always 1/2 of what I've added to s. So I can say the sum from q, we start from 0 to infinity, s to the delta plus q, chi, q over 2, theta left, chi, q over 2, theta right. And that's the guarantee. And you calculate them all like that. It's just a trace of a matrix. Okay. Now, this answer is wrong. Why is it wrong? What did I do wrong? So we started off with O. Okay, sorry. This answer's nearly always correct. So let me ask you another question that's maybe something. The delta is equal to 1. that answer's wrong. Can anyone tell me why? Let's take a look. We start off, we had our operator O, then the first descendants was P mu O, so we added a contribution to the character of that state, of those states. Then we added P mu minus eta mu nu over D, where before P alpha O, and then we added P alpha O, and then we went going on. Have we made mistakes somewhere? Is there a brave person who wants to make a guess? What did you prove yesterday in the tutorial?
That this was
About this
zero space.
null state. Absolutely. This is a null state. What does that mean that that's a null state? It means the following. Okay, so let's take that null state. If we take, so let's call this the null state psi. Everyone agrees psi is equal to 0. That's what you proved yesterday using the algebra, right? Now, if we take psi e to the I t d plus I beta left j3 left plus I beta right j3 right psi, then the j3 right eigenvalue is naught, the j3 left eigenvalue is naught. This lands up giving us s to the delta plus 2, but then it should be multiplied by psi. And I just keep assuming up to now that psi is 1. But we proved yesterday psi is naught. So this is wrong. A whole lot of the states that we added, we shouldn't have added. Okay? So what we need to do is, we need to subtract this state and all of its descendants. What would the sum of the state plus all of its descendants be? So, we must subtract this state, which is delta is equal to 3, j3 left is equal to naught is equal to j3 right, and all its descendants. But actually, if you sum the contribution of all of those to this trace, that is a character. That's the character for delta is equal to 3, and spin naught for j3 left and spin naught for j3 right, because we've just summed over the states inside a full representation. This thing now looks like a primary. It is a primary. K kills that state. Null states are primaries, plus all of its descendants. So whenever you want to subtract out the contribution from a null state, you're always subtracting out another character. So it turns out that for one naught, what this is equal to, you have to take that formula over there. So let's say the sum from P and Q is equal to naught to infinity. You plug in a 1. P plus Q plus 1. And you will subtract off what you get when you plug in delta 3. So that corresponds to 1 minus s squared. There I'm subtracting off the operator with a dimension 2 larger than the one I got. And then I have chi q over 2, beta left, chi q over 2, beta right. And that's the general story of calculating characters for the conformal. The only thing you have to worry about is sometimes you'll have a null state. For the specific character that we're interested in, we do have a null state, so we have to take that into account. Now, there's a nice formula for the character. So we don't have time to prove it. It's actually not so difficult to prove. But what I'm going to suggest to you guys to do, try to prove this. See if you can prove it. If you think in the right way about it physically, you'll be able to just write it down. And if not, expand it out. It's a bunch of denominators that you have to expand. You'll get some formula. Okay. All of the results I'm showing you were only derived in the last 10 years or so. So this is quite an old subject. Surprising it took so long. And the key formula that allowed people to make the progress is the one that I'm going to write down now. And it's a pretty simple formula, but just no one had realized it. And it is the following. You see, this sum looks a bit unwieldy, but we can actually do it. The sum on P and Q is equal to 0 to infinity of S to the 2P plus Q chi Q over 2. I'm going to call this X chi Q over 2Y is equal to 1 over 1 minus S e to the I x over 2 plus I y over 2. 1 minus S e to the I x over 2 minus I y over 2. Okay. 1 minus S e to the minus I x over 2 plus I y over 2. 1 minus S e to the minus I x over 2 minus I y over 2. Okay, that's the sum. Let me give you one hint if you want to try to prove this. It's actually much easier to prove than you might think. What are you doing? Okay, so if you've got 1 over 1 minus x, what is this equal to? This is equal to 1 plus x squared plus blah, blah, blah. How many components of the momentum do we have? 4. So you can think about this is x, this is P0, P1, P2, P3. If that were the case, when you expand this out, you're going to get all possible products of the different p's appearing. And that's what multiplies the operator. What's the dimension of p? 1. That's why you have an s appearing there. What's the spin of p? 1/2, 1/2. So if we go through the states, what possible spin states could we have? Spin a half and spin a half, both. This is spin plus a half, this is spin plus a half. Here, spin plus a half, spin minus a half. Here, spin minus a half, spin plus a half. Here, both of them are spin minus a half. And that's why when you expand this thing out, you reproduce precisely that answer. So with a little bit of thinking and that hint, at first it might look a bit tricky, just think about it, you'll get it. Okay. Now, let's now prove what's called the Flato-Francois theorem. So we're going to take a tensor product of 2 of these characters and let's see if we can work out what's going on. So we want to take chi1 naught naught times chi1 naught naught. By the way, if anybody wants a research project, if you can take this character to the nth power and decompose it into representations, you can publish it. Not for 2 and 3. So what does this look like? So I'm going to write the first character as s 1 minus s squared sum phi and q is equal to 0 to infinity s to the 2p plus q chi q q over 2 of x, chi q over 2 of y, multiplied by. Now I'm again going to write s, 1 minus s squared, but I'm going to recognize that this whole object sitting over here is nothing but this quantity. Let me call this p of s, x, y. This is p of s, x, y. Something else that I want to make clear is the following. Chi delta naught, let's keep this. This was s to the delta multiplied by that sum. Okay, infinity s to the p plus q chi q over 2 x chi q over 2 y. And this is s delta of p s x y. And notice, where does the primary quantum numbers appear? As something multiplying p. In fact, for a general character, you will have the following. If you've got chi delta s1 s2, what this looks like is s to the delta chi s1 of x chi s2 of y multiplied by the same p. And that's the general character. This is built on a primary operator with dimension delta and spin s1 compressed. And that will be the general character. Good. So now let's manipulate this a little bit. And I'm just rewriting this as follows. So I've got an s squared p plus a sum, and q is equal to 0 to infinity. So you just have to interpret this a little bit, and we will do that. 1 minus s into times by s to the 3 plus q. I shouldn't write that. S to the 3 plus q chi q plus 1 over 2 x chi q plus 1 over 2 y minus s to the 4 plus q chi q over 2 of x chi q over 2 of y times by I did nothing fancy here, I just rearranged the terms. That's all I've done. Now, we have to take a look at this formula and interpret it. And there's a nice interpretation. So let me re-output it here. So we've got 1 naught naught tensor 1 naught naught is equal to, and if you look here, we've got s squared p, but s to the delta p is just a character. So we've got the character dimension 2 with spin naught plus. Now we have a whole bunch of things. But look what's happened. We've got s to the 3 plus q. Then we've got chi q plus 1 over 2, q plus 1 over 2, minus, and this thing sitting over here. Now when you get minuses appearing, you could never get a minus from the trace. The trace was the exponential of something and you were summing. So whenever you have a minus, you're being told there's a null state. But what is this null state? Actually, you can form operators of this type in the theory. So let me give you a simple example. Let's look at J, mu, nu. This, for example, would be an operator of spin 1, 1. So I'll make it symmetric traceless. What it would look like is d nu phi, phi, minus d mu phi, d nu phi. This thing is called a higher spin current. Because this is a free theory, there's an infinite number of these conserved currents. So what you can check is d nu, j mu nu is 0. It's conserved. But what was momentum? Momentum was p mu. So this is telling you one of the descendants that you form actually vanishes. This is telling you there is a null state. This had spin 1, 1 because of 2 indices. How many free indices does this have? Just 1. So this would be 1 half, 1 half. Each of these spin labels has decreased by half. Now take a look. Q plus 1 over 2, Q plus 1 over 2, Q over 2, Q over 2. The dimension here was 3 plus Q. The dimension has increased by 1. And here the dimension increased by 1 because you had the derivative that was coming from the momentum. So in actual fact, what our answer is, this is now a sum from Q is equal to 0 to infinity. The dimension is 3 plus Q. And the spin is Q plus 1 over 2, comma, Q plus 1 over 2. There's only one known consistent theory of quantum gravity, higher spin type theory. And if you go ahead and work out what is the spectrum of fields that you get for that theory on ADS5, this exactly describes that spectrum. So this would be your first hint that a conformal field theory is dual to a theory of quantum gravity. Okay. And this is what's called the Flatter-Franz-Dahl theorem. Okay, good. So I think I'll stop with that. Are there any questions on that? Sorry we didn't get to calculate any anomalous dimensions, but, well, I don't think I should have gone faster.
I think that was so fast I mass community. Would you repeat?
Sure. You mean this discussion?
Yeah, from the interpretation of that formula.
Good. When I see the minus sign, whenever you're calculating character of this type and you see a minus sign, you should think you've got a null state. Okay? And I'm giving you an idea of what that null state looks like. You can see I've defined a current here. Now what you can check is in the free theory, this current is conserved. And why is that? You know that you've got the massless Klein-Gordon equation. So when you hit d mu on this term, you naturally get 0. When you hit d mu on this term, it will cancel against when you hit d mu on that term. And when you hit d mu on this term, you get 0. So this thing is conserved in the free theory. Okay? What that means is, when you want to calculate one of the descendants, d mu on j, you'll get 0. So this corresponds to a null state. And we said every time we have a null state, we must subtract off the character. Now, if the current has dimension whatever, the null state has one more dimension. 3 plus q minus 4 plus q. The dimension is increased by 1. Here there are 2 indices, so that gave me 1, 1. Here there's one less index, because there's just a new free. So each of these 2 spins will decrease each by 1/2. Happy? Good. Any other questions? Okay, guys.